University of Rio Grande do Sul in Porto Alegre, Brazil, in 2001, and has Master of Science also from the same university in 2006. He is presently at Hatch in the Center of Excellence for Aluminium in Montreal, Canada, and he's consultant there. His work experience, for several years, 5 years, he worked at PC Limitada in Porto Alegre, Brazil. And since 2008, he is at Hatch in doing also a lot of simulation. And this afternoon, we have very interesting papers in simulation. So I would immediately pass the word to André Felipe.
So thank you, Vinku. It is once again a big pleasure to be here in front of you once more, and especially after this kind introduction by my old master here. So let's start with a brief safety share. If something happens, it will not, but if it does, we're going to exit through these doors and we're going to follow the signs leading to the meeting points. I would also like to acknowledge, first of all, our host, and after that, our corporate members and conference sponsors, because these companies, our industry, is what makes this conference possible for all of us. So thank you, EGA, thank you, sponsors, thank you, our corporate members. It is very kind of you and very appreciated. Our first speaker in this afternoon is our dear friend and colleague Marc Dupuis. Please, the next slide, please. Whoop. There. Dr. Marc Dupuis obtained his PhD in chemical engineering in '84. And since 1994, he is with his own company, Genesim, where he has been consulting for many of us throughout the industry, and he has helped to design, improve, and help our design efforts for many different technologies. His work experiences in mathematical modeling and the design of cells, dealing with the thermoelectrical, thermoelectromechanical, CFD, and MHD phenomena. So please welcome Marc Dupuis.
Thank you, André Philippe. Okay, so my title is in back. Okay, so my title is Cathode Effect in MHD Stability. So it is an application of MHD Valdis. That is the code I'm distributing. So this is a kind of a practical example of a model development and then application. So the idea is that this code is on the market for about 20 years. And it's still on continuous development, and the most recent development is improving the way we represent the current passing through the cathode, and then from that we can achieve a bit more flexibility in type of design. Then I will compare, because I wanted to make sure that we are doing a good job with the new code version, I'm comparing with ANSYS, and then I will present some example of the application. So it started in the 60s. Gevry was the first to try to do this kind of calculation, and he was using a network of resistance like we see here, horizontal and vertical. Now MHD Valdis, he was only doing vertical up to this code version. So we'll see what the impact it has on the result, and after that I will introduce more change. So MHD Valdis look like this. It is the thermoelectric part is a bunch of 1D conductor, and we have the ferromagnetic, but I'm concentrating on the electric part now. So we have the standard definition MHD Valdis is using is a line element for conductor, including in the cathode. And so that's mean that you have some option what to do. And then as comparison, you can use ANSYS, finite element, and then here I will compare with this type of model that I published first in 1994. It is, you build a parametric model where you define the geometry of the cathode, the collector bar, and the anode, and then you get this kind of model. It is, of course, more accurate because it's a true geometry, and you can have properties that are temperature dependent. So it's a good comparison. So what have changed between the code version? The old code, he was assuming only a linear conductor only going vertically down. So the cathode was essentially a series of tube of carbon, and with no horizontal possibility for current to travel horizontally. And then he was not bothering with asking for the cathode's size because we were using the ledge toe as a boundary condition. So any line conductor blocked by the ledge was not carrying any current. And now that in that code version, we have introduced horizontal conductor. So now the size of the block is important to specify. The way also the contact resistance was applied is only by one number. So that means it had to be uniform. And here you have some detail about the geometry. You have 31 elements in MHD Valdis through the width of the cell. And that's important because now we are shifting to this kind of input. So here you have on top, whoops, on top here you have the length of the block. That is the wrong length, but for comparison, I'm using this for this part. And you have to redefine the contact resistance here. That is defined in ohms, so you have to account for the size. And here I won't go into detail because I have 10 minutes left. And I will, that's the number that you need. Oops. That's the number that you need to represent the same contact resistance as in the previous input. So you get a solution. On this side, it is using the old input, and then this side, the new input. And then here you get new result is the horizontal current traveling in the carbon itself. And the cell is the 3-met cell that we are using, for example, all the time now. And this is the wrong solution because now the block is not that long, and you don't get the. You don't get as a result the right current density in the metal pad. That is what we're showing here. Oops, tricky this thing. So this is the representation of the horizontal currents in the y direction with the old input and new input, and those are both wrong solution. But if you use the old code with the old input, of course, you're getting this solution that is very different. About half of the horizontal current, and this is more like the right solution. But this old input was limited, as I was saying. You have to apply only one uniform contact resistance, and then now we are trying to be more flexible. So yes, so now I will present some example and we'll compare with ANSYS. So this is the ANSYS representation of the 3-met cell. And this is the ANSYS solution for this geometry. We have a prediction of CVD, we have a prediction of the maximum horizontal current. And as you can see, it's quite close to what the old code was giving. And now this is the new input. So now I'm setting in the right value for the length of the block, and then I'm readjusting the contact resistance based on this new geometry, so new surface area for each element. And then I'm getting this solution that is now very close to an ANSYS solution. So here we have MHD Valdis, and here we have ANSYS. There's still a little discrepancy. Then, because I faced this discrepancy, I wanted to investigate more, and then the next improvement will be explained in the TMS paper. But it's not the limitation of the code. It was a limitation in the property that we used. Okay, so now I'm saying it is MHD values was not really designed to give only the current density in the metal pad, but it's convenient because it's very quick to obtain, and it is parametric, so it is very quick to get the input in the model to get a solution. So it would be nice to be able to rely on this, and so that's why. By doing the comparison, you can feel comfortable to use this as a first, let's say, a quick solution to if you want to experiment option. Here I'm going to give some example of what you could try to do. So the first is to try incomplete bar rodding. So here I use now the new flexibility to remove any contact in the last 3 units. And then that's representing removing the last 10 centimeter of cast iron from when you rod. It is something that has been done by the last 40 years, like AP18 was already doing this. And this could not be represented in MHD values up to now. And this, so here I'm comparing, you can do the same in ANSYS, and then you get the two solutions. And again, you get a fairly good match for the horizontal current, not so good match for the CVD and the TMS. I will show you that I can do better than that now. But MHD values was never really meant to be accurate on CVD, but now that we can compare more easily, you can investigate and then fix this issue. Okay, here I'm trying something different yet again. It is in selective rodding that I presented this paper in 2000. So you stop casting in some section. So you cast here, and in between you put some insulating material, some cement, and then you can get a very uniform current density on your block surface. That's one way to achieve this, or getting rid of horizontal current. So here I'm showing the MHD Valdez solution. It's almost completely removing the horizontal current in the y direction. This is the color coding, is the y direction of the horizontal current. But if you can see, as in the arrow, I have some X component because of the geometry of the 3-met cell. And then that will become important for what I will present soon. So remember that I got rid of the horizontal current in the y direction by selecting rodding, but not in the X direction, because it's of course not affecting the y. The X direction is affected by the geometry of the anode panel and then the geometry of the ledge. And then in the 3-met cell, it is not really matching well. Okay, so now that we have obtained the horizontal current, we can go to the full transient analysis. That is the purpose of MHD values. So here I'm comparing two solutions. The first one is the standard, let's say, when you fully rod up to the edge of the block, and at 4.3 centimeter ACD, we are getting a kind of a critical stability. The perturbation is about stable. And if you do the partial rodding, at the end you don't rod the last 10 centimeters, you can see you're getting a damping, so that means that now the cell is stable, and so this is what you get as a solution of an MHD stability study. So to give you an idea, because my next paper coming next is is a way to get this solution faster. This is about 24 hours CPU time involved in those two curves, 12 hour and 12 hour in each, because it's about the time it need to produce this solution. And now I'm presenting one more here. Here I'm comparing selective routing and incomplete routing. And to my surprise, initially, I'm getting about the same stability. So it means that the further reduction of the y direction horizontal current did not improve the stability. And our explanation was because we have all this x direction horizontal current that we cannot improve. And then I will confirm that at the TMS. I'm getting presenting future result. Okay, and here you can also use MHD Valdez to get an answer to the question how this impartial routing, not routing the last 10 centimeter, represent as ACD. And so we have decreased the ACD until we get again critical stability. And the result is 2 millimeter of ACD that you gain by this 10 centimeter impartial routing. So I'm ahead of my time. It's not bad. This thing is good. So conclusion, I presented a new version of MHD Valdez with more flexibility. With this new input parameter, input file, you can now do things like impartial routing or selective routing, or you could even have, if you can achieve to do that, contact resistance that evolve along the length, all kind of thing you can try to do, then you can investigate in MHD Valdez. And then we have here, we have seen some example of what you could do with this new flexibility. Thank you very much for your attention.
Thank you, Mark, for your presentation. And now questions from the audience. Alex?
Thank you, Mark, for your presentation. First of all, I want to say that we use this model with horizontal current cathode block already for a couple of years. I don't know why it is new, because we also has concern about this and ask our Valdez to implement this. Also, we use different properties of collector bar, which I think should solve the issue with also not correspondence of CVD between ANSYS and MHD Valdez. But I heard about new feature of cast iron. This is good improvement. My question, I didn't understand from your graphs, because it's from this legend, when you insulate, let's say, when you have no casting at the end of collector bar, you get better stability or worse stability?
Better.
Better. This was 2 millimeters of ACD reduction.
Well, at the end is that I decrease as ACD to get back to critical stability that I had before doing incomplete routing. So that's mean that not routing the last 10 centimeter represent 2 millimeter ACD according to MHD values.
Okay, thank you.
Good afternoon. This is Share from GAMI. I have a question on the new software. You have mentioned that for the cathode routings, you're having some particular, you can say that the modeling ways to simulate. And right now we're having the copper inserted collector bar, or if we're having some the cross-section variance collector bar, that means that the cross-section is a variable. So it's like that. In the center of the cell, the collector bar section is large, and in the side, it might be reduced. So do you have any modeling solutions for these kind of cathodes?
You mean to model it? In MHD Valdez, it's not an option to have a variable section of copper insert. But obviously, in ANSYS, you do whatever, you enter the geometry you want. It is up to you to create the geometry and then solve the problem.
Okay, so the simple answer is that you can model the copper insulated collector part, but not the cross-section virus collector
In
part.
MHD Valdis, because it's a closed program, you have parameters to, so you can define in the file the size of the copper insert, and there's no provision for having it to change along the length. No.
Okay.
Yeah.
Thank you. Thank you.
More questions from the audience? I have one.
Yes.
We got an offset of maybe 30 Celsius, 30 millivolts between
Yes.
between MHD and ANSYS, and I know that your model in ANSYS did not took into account the pot-to-pot busbar circuit.
The what?
The pot-to-pot busbar circuit.
No.
No.
You have seen it. Yeah.
Do you believe that this is one possible cause for the mismatch in voltage drop?
It's part, you could, yes, because of course MHD Valdis give the average value of each, because it's computing each of the single one, taking into account the busbar network that you have defined around it. And then in ANSYS, it's a fixed boundary condition, so you assume a uniform current collection. So yes, it is part of some discrepancy potential, but I found another issue about property that yes, I was not using exactly the same property for both models.
I'm eager to see what you're going to present in March. Time for one more. Well, in this case, let us thank Mark for the great presentation.
Thank you.